Okay, YouTube, this is my second video in which we're going to use the shortcut formula for finding sample variance and standard deviation, but not for raw data where we actually have the data set, but for grouped data that's already been organized into a frequency distribution for us. So just going to kind of go through how this is very similar to finding standard deviation and variance for raw data in terms of what you need to find here. So our shortcut formula, recall, is this here. We say since it's for a sample, we use this lowercase Roman letter s squared, and this represents our sample variance. And then the idea is this: if we want the standard deviation, recall that the standard deviation is just equal to the square root of what the variance is. So for the variance, we need three things, okay? We need to know how many data there are. We need to know what the sum of the data is, and also what the sum of our squared data is. So you'll notice the difference here is this. We say the frequency times the class midpoint is the sum of our data. The frequency times our squared class midpoint is the sum of our squared data. So knowing these three things is going to allow us to find everything we need here. And I just want to point this out. Anytime you talk about a frequency distribution, usually the first thing you do is you calculate the mean anyways. So when you calculate the mean, what do you need to know to find the mean? You need to find the sum of the data and how many data there are. So those are two of the three measurements we already need to find variance and standard deviation anyway. So let's go ahead and consider this data set. It says the cost per load in cents of 35 laundry detergents that were tested are shown in this distribution below. So you can see these classes here. It seems that the cheapest class started at 13 cents and the most expensive class ends at 68 cents, and it looks like we have a class width of, let's see, 13 to 20 here. Looks like it's going up by 7 in each class. But essentially we have like two detergents that were somewhere between 13 and 19, 7 between 20 and 26, and 12 between 27 and 33, and so on and so forth. If we want to calculate the mean, we need to go ahead and determine two things here. And assuming this is a sample, so we use a lowercase n, we need to find how many data there are, and we need to find out what all of the data add up to, which is going to be this value right here. So in terms of how many data there are, well, this is as simple as reading the problem. There were 35 data, as a matter of fact, but if we didn't know this, we could just add up all the frequencies here. We say 2 plus 7 is 9, plus 12 is 21, plus another 5 is 26, 26 plus 6 is 32, 33, 35. So we're going to go ahead and scribble this down. What we come up with here is this. We have 35 different detergents. So we say 35 different detergents. So I'm going to go ahead and abbreviate that there. Now, what does our data add up to? The thing is, I don't have the original data set. So what we're going to have to do is we're going to assume that since I don't know what these two actually cost in this lower class, lowest class, we're going to assume that it's perfectly between 13 and 19. So in other words, we are going to assume that they are the class midpoint. So you'll notice my table has 4 extra columns built on here. The first one here is going to represent what would the midpoint of each class be. So the midpoint of 13 and 19. Please recall that if you want to find the midpoint of two numbers, all you need to do is add them together and divide by 2. In other words, we are going to find their average. So we say there's a 16-cent midpoint in this first class. And I also know this: since every class has a width of 7, we're just going to go up by 7 every time on this number. So if I were to add 7 to this, I would get to the next class midpoint that intuitively I would think would be 23 here, but 16 plus 7 does indeed come out to be 23. So I'm going to keep adding 7 to each class midpoint just to kind of arrange our next class midpoints. This be 44. And then we add 7 to that, we get 51 cents. Add 7 to that, we get 58 cents. And add 7 to that, we get 65. And I always like to check to see if these numbers or values are reasonable with my classes here, and it looks like they are. So in terms of what do all of our data add up to? Well, assuming that two detergents were 16 cents each, that would add up to 32 cents on their own. This second column that we added on here is going to be our frequency times the class midpoint. So you notice when I write the sum of our data, I'm really writing the sum of each of these individual classes, what they added up to. So 2 times 16, that'll give us our frequency times our class midpoint here, and those would individually add up to 32. So this class adds up to 2 16s, it's 32. We have 7 23s. That's 140 plus 21 more. Would be 161. I should probably use a calculator here, but some of these I can dig out on my own. We say this would be 360 here. 5 times 37 would be 150 plus another 35, so 185. Let's see, 6 times 44, that'd be 240 plus another 24, so it'd be 264. 1 times 51 is 51, 0 times anything is 0, and then 2 times 65, well 2 times 60 is 120, and 2 times 5 is 10, so 120 plus 10 is 130. So now that I know what each individual class's data added up to, what we're going to do is we're going to sum up all of these, and I usually like to write the sum below this. You can see I have some text in the way, but we're going to write that sum here, and so this is why we need our calculator now. So looks like we get 32. Let me clear this out. We have 32 plus 161 plus 360, so 32 plus 161 plus 360, I was going a little too fast there, plus 185 plus 264 plus 51 plus 0 plus 130. So those all sum up to 1183. So we're going to write that sum here. We say 1183 cents total. This is how many total cents. So if we want to find the mean, recall that the mean for sample data, we use Roman letters to represent sample statistics. So we say X bar is our mean. We should always write this as a ratio first before you write the mean. So we're going to find this value on our calculator, keeping in mind that when we find this on the calculator, 1183 divided by 35, we are going to carry this out to one extra place value than what the original data went out to. And it seems that we carried the original values out to the nearest whole number, so we'll just take this out to the nearest tenth, which it gave us. So we would say that this comes out to be 33.8, and I'm going to write cents. I'm not going to write the symbol for cents, but basically we can say that the average load costs, given this distribution here, about 33.8 cents. And that makes sense, no pun intended, but 33.8 cents would be somewhere around these two classes-ish here. And you can see that we were really heavy with data in this middle portion right here, where it's kind of sparse as you move away from the average. So the average, is located towards the center. So now, the whole point of this video was to go through and calculate the variance and standard deviation for grouped data. However, what I wanted to do was highlight the fact that you need these two values first. We need these. We got to have them, okay? Because our shortcut formula demands that we have them. We need n, and we need the sum of our data. Okay, so now the only thing we don't have is this frequency times squared class midpoint. So essentially what we're going to do is we're going to go back and we're going to say, well, what would happen if I added together my data, but that I squared? So we're going to have to take all these class midpoints and square them. And there's only one of these I can do in my head. 16 squared is 256. So we're going to need a calculator for these. And this calculator here, we're going to pull this out and we say, let's take our class midpoints and square them. So we say 23 squared gives us, let me clear this out. 23 squared is 529. Okay, so I lied. I can do this one in my head. 30 times 30 is 9 with 2 zeros after it. 37 times 37, I certainly don't know. So we say 37 squared, we get 1369. So you can see how when you're dealing with variance, you get big numbers really quickly. We say 44 squared. 44 to the power of 2 is 1936. That's kind of fun. Look at that. They transpose digits. 51 squared. 51 times 51 is 2601, so 2601. 58 squared, we need to square our 58 here, so 58 squared is 3364, so 3364. And then last but not least, we say 65 squared. So 65 squared, we get 4225. So now that we have all of these midpoint values that we've squared, we need to add in our last column here, which is our frequencies, not times the data, but frequencies times the squared data. So we get to go through, and we're going to take this entire frequency column right here, this time times our squared data column. We're going to multiply these values. So 2 times 256 is going to be 512. We get 7 times 529. Whoa, okay, so I don't know this one. 529 times 7. We get a value of 3703. So we get 3703. This time we're going to take 12 times 900. So 12 times 900, I believe is 9600, but 12 times 900, I think I'm wrong here, 10,800. So 10,800, 10800. So we're going to take this 5 now times 1369. So 5 times 1369 times 5, 6845. I'm trying to do this as quickly as possible. 6845. We'll take the 6, which is the frequency, times 1936. So we have 1936 times, we have a 6. So 11616. So 11616. Now we're going to take 2601 times 1. Ooh, I can do that one. 2601. And we say 0 times 3364 is 0. And then last but not least, 2 times 4225. I think I can get this one, 8,450. So now what we need is the sum of our squared data, that is frequency times class midpoint squared. We get a sum here, and that sum comes out to be the sum of this entire column. So adding all of these up here, let's do this. We say clear 512 plus 3703 plus 10800 plus 6845 plus 11616 plus 2601 plus 0 plus 8450, and we get a grand total of 44527. So 44527. So now the nice thing about this is we can scratch together our variance first, or sample variance, which recall is this. It's n times the sum of the squared data minus the sum of the data squared over n times n minus 1. Since it's a sample, we have to take n times n minus 1. So I'd like to fill in our n's first here. I'm kind of partial to doing that. And so we say n. In the first case, we had 35 detergents. So we had 35, 35, and I would take 35 times 35 if this was a population, but it's 35 times 34 since we're talking about a sample. And in terms of what values go here, we know that we're plugging into this formula here where we have the sum of our squared data minus the sum of our data squared. So that's why I put the squared on the outside on this one. We're going to drop in our bigger of our two values, is always the front one here. We have to have a positive output for variance. So 44527. And then the second value was the sum of our data we already had up here. And so now all we have to do is carry out this calculation. So what I end up with is this. Starting with 35 times 34, we get 1190 in the basement, so 1190. And then on the top, we'll go ahead and carry this out. We say clear 35 times 44527. This first value here is this giant number. We say minus now 1183 squared. We get a difference of 158,956. 158,956. So what this comes out to be is our sample variance. So we're going to take this divided by 1190, and we get 133.576. I'm actually going to write 133.576. Keeping in mind that this goes on forever and ever. So I'm going to put a big fat box around this because what we have just discovered is our variance for our data set. Since we want the standard deviation though, we say S is our standard deviation. That is the square root of S squared. And so we get approximately, now the nice thing about leaving this up on your calculator, don't clear it, is because we're going to take the square root of this number we just found. I'm going to hit the square root key, and we get 11 point, this decimal right here. Since, again, our original data went out to the nearest whole number, we're going to go out to the nearest tenth. So 11.55, we're going to round off to this 5. It'd be about 11.6-ish. So we say 11.6-ish, and we're going to label this cents. So the reason why we wanted to know our average and our standard deviation is because of this. If we look at this histogram here. Now, what you see is the frequency distribution graphed here is a histogram, and this is the cost per load in cents, where this is how many detergents lie in each of these classes at the bottom. So you have money data at the bottom and how many things lie within these certain class ranges here. What I want to do is I want to ask some questions about this. So we say, first of all, looking at this histogram that I provided, what shape does this distribution have? And I notice that it goes up. If I could draw on this here, I think that I might have to adjust this. But maybe not. Maybe not. Maybe I can draw on it now. I can. I notice that it kind of has a bell shape, but it has this long tail off on the right. So I would say that this is a right-skewed data set. And the reason why I'd say is right-skewed is because it's approximately bell-shaped, or perfectly bell-shaped would look like this, but it has a tail on the right side. So it's a bell shape with a tail on the right. Other things I want to mention. Well, the average was 33.8 cents. So where would the average lie on this distribution? Well, it'd have to be somewhere here in the middle. And you notice that 33.8 is around this 33, 34, so the average would be around right here. We say this is my X bar. So now, in terms of standard deviation, our size of our standard deviation was give or take about 11.5-ish cents. So basically, things, if the average is about 33.8, we're saying if I were to take 33.8 and add on about 11.6 cents, we'd say 45.4. That would be, say, around here. And if I were to take now 33.8 and subtract off a standard deviation, which is 11.6 cents, is about 22.2. That's about right here. We're saying that most data on average lies within this range either way, okay? So the size of our standard deviation gives us the average spread of our data here. So the questions I want to finish up with are these. It says the provided histogram shows the data distribution, what it would look like if the last class were thrown out. What if we were to throw out the last class? So you'll see here that this last class, basically, if we were to throw this data out, okay, that is, this would be gone, okay? What would that do to our mean? What would that do to the average? And basically what you could say is, well, if you threw out the expensive ones, what's going to happen is our average is going to decrease. So we would say that the average or the mean would decrease. And then my next question is, well, what's going to happen to the standard deviation? The standard deviation is the spread of our data, or the average spread of data. So since we got rid of some data that was really far away from the average, what's going to happen is our squared data values are going to decrease because we didn't have anything down here, which means our variance decreases, which means our standard deviation decreases. But in general, we're saying that our data would basically be more packed together. So the standard deviation would decrease. And in other words, we would say that the data is more packed around the mean, okay? And then also this, I asked this question here, what if the data in the first class was thrown out? What would be the effect upon the average? So again, what if I said, imagine this, what if we threw out this data? In our table up here, basically, we would have had no frequency in the first class, so, we would have nothing here and nothing here. What would happen is, again, our average, since we threw out inexpensive things, our average would probably go up again. So our average would probably, be somewhere here in the middle, X bar. But what would happen to our standard deviation? Again, our standard deviation would decrease because now our average spread of our data went down because data is now even more packed around the average because we're getting rid of things on the outside. Cheers.